Scientists just discovered something that shouldn't be possible: galaxies at the edge of our vision that are older than the universe itself, structures so vast they break our models of physics, and a cosmic horizon beyond which lies something so incomprehensible that even speaking about it challenges the very nature of reality. But here's what will truly haunt you. Everything we can see, every star, every galaxy, every cluster, stretching billions of light years in all directions, might be nothing more than a microscopic bubble in an infinite ocean of existence. Today, we're about to confront a truth that will fundamentally shatter your perception of reality. The universe isn't just bigger than you think. It might be bigger than it's possible to think. If you're fascinated by the mind-bending scale of our cosmos and want to explore more incredible mysteries of space, make sure to subscribe to this channel and give a thumbs up. And here's something I'm curious about. If you could instantly teleport to any location in the universe, but you could never return to Earth, where would you go? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. Let's start with what we can actually observe. The observable universe, that's the sphere of space from which light has had time to reach us since the Big Bang, stretches about 46 billion light-years in every direction from Earth. Wait, you might be thinking, if the universe is only 13.8 billion years old, how can we see things 46 billion light-years away? Shouldn't the maximum be 13.8 billion light-years? This cosmic puzzle confused even brilliant scientists for years. The answer lies in the expansion of space itself. When we see a galaxy whose light took 13 billion years to reach us, we're seeing it as it was 13 billion years ago. But during those 13 billion years, while the light was traveling toward us, space itself has been stretching, carrying that galaxy much farther away. It's like watching someone walk on a moving walkway at an airport. They're walking toward you, but the walkway is carrying them backward even faster. The most distant object we've ever observed is a galaxy called GNZ11, discovered by the Hubble Space Telescope. Its light has been traveling toward us for 13.4 billion years, meaning we're seeing it as it was just 400 million years after the Big Bang. But due to cosmic expansion, GNZ11 is now about 32 billion light-years away from us. Think about that. We're looking at baby pictures of a galaxy that's now an unimaginable distance away. But here's where things get even more extraordinary. The observable universe is almost certainly not the entire universe. It's just the portion we can see, our cosmic horizon. Just as standing on Earth you can only see to the horizon due to the planet's curvature, we can only see to our cosmic horizon due to the finite speed of light and the age of the universe. Beyond that horizon, there's more universe we simply cannot observe. The cosmic microwave background radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1964, gives us the most distant view possible. This faint microwave glow filling the entire sky is the cooled remnant of the Big Bang itself, the oldest light in the universe. The Planck satellite, launched by the European Space Agency, has mapped this ancient light with incredible precision, showing us the universe as it was just 380,000 years after the Big Bang. What Planck revealed was astonishing. The cosmic microwave background is almost perfectly uniform in all directions, varying by only about 1 part in 100,000. This uniformity tells us something profound. The universe is incredibly smooth on the largest scales, and more importantly, it appears to be geometrically flat. Not flat like a pancake, but flat in the sense that parallel lines remain parallel forever. Triangles have angles that sum to exactly 180 degrees, and space doesn't curve back on itself. This flatness is crucial for understanding the universe's true size. In a positively curved universe like the surface of a sphere, space would be finite but unbounded. You could travel in one direction, and eventually return to your starting point. In a negatively curved universe like a saddle shape, space would be infinite. But in a flat universe, which is what we observe, space extends forever in all directions. The Wilkinson Microwave Anisotropy Probe, or WMAP, which operated from 2001 to 2010, confirmed these findings with even greater precision. It measured the universe's geometry to be flat to within a margin of error of just 0.4%. This means that if the universe is curved at all, the curvature is so slight that the universe must be at least 250 times larger than the observable universe. But measurements from different methods paint an even more staggering picture. Analysis of the cosmic microwave background's patterns suggests that if the universe is finite and curves back on itself, it must be at least 1,000 times larger than the observable universe in diameter. That would make the entire universe at least 1 billion times larger in volume than what we can see. And that's just the minimum. It could be infinitely large. The inflationary theory, proposed by Alan Guth in 1980, suggests the universe underwent a period of exponential expansion in its first fraction of a second. During this cosmic inflation, the universe expanded by a factor of at least 10 to the 26, that's a 1, followed by 26 zeros. This mind-boggling expansion would have taken quantum fluctuations and stretched them to astronomical scales, creating the seeds of all the structure we see today. If inflation happened as theorized, the actual universe could be 10 to the power of 10 to the power of 30 times larger than our observable universe. That number is so large that writing it out would require more atoms than exist in the observable universe. Speaking of mind-blowing scales, if you're fascinated by cosmic sizes, you should check out my video "We Just Found Out How Big the Milky Way Is," where I explore the shocking discoveries about our own galaxy's true dimensions. The link is in the description below and on the card above. Now let's zoom out even further to grasp the universe's true immensity. The concept of eternal inflation, developed by physicists like Andrei Linde and Alexander Vilenkin, takes things to an even more incomprehensible level. In this model, inflation never completely stops. It continues forever in most of space, with only small pockets dropping out of inflation to form bubble universes. Like our own, if eternal inflation is correct, then our entire observable universe, those 46 billion light-years in all directions, is just one tiny bubble in an infinite, ever-expanding multiverse. New universes are constantly being born, each potentially infinite in size themselves. But how do we even begin to measure something that might be infinite? Scientists use several ingenious methods. One approach involves looking for repeating patterns in the cosmic microwave background that would indicate if space curves back on itself. Imagine being inside a hall of mirrors. You'd see repeated images of yourself. Similarly, if the universe were finite and small enough, we might see repeated patterns in the cosmic microwave background as light wraps around the universe multiple times. The Planck satellite searched extensively for these telltale patterns and found nothing. No repetitions, no ghost images, no signs that we're seeing the same regions of space from different directions. This null result is actually a profound discovery. It means that if the universe does curve back on itself, it's so large that light hasn't had time to wrap around even once in 13.8 billion years. Another method involves studying the largest structures in the universe. The Sloan Digital Sky Survey has mapped millions of galaxies, revealing a cosmic web of filaments and voids stretching billions of light-years. The largest confirmed structure is the Hercules Corona Borealis Great Wall, a galactic filament roughly 10 billion light-years long, more than a tenth the diameter of the observable universe. The existence of such massive structures puts constraints on the universe's size and age. In a smaller, younger universe, there wouldn't have been time for gravity to build such enormous formations. Dark energy adds another layer of complexity to our cosmic size estimate. Discovered in 1998 through observations of distant supernovae, dark energy is causing the universe's expansion to accelerate. The Dark Energy Survey, using the Blanco telescope in Chile, has confirmed that dark energy makes up about 68% of the universe's total energy density. This accelerating expansion means that galaxies beyond a certain distance are receding from us faster than the speed of light, not because they're moving through space that fast, but because space itself is expanding between us. This creates what's called the cosmic event horizon. Right now, galaxies more than about 16 billion light-years away are receding faster than light speed. We can still see them because we're looking at their past, when they were closer, but any light they emit today will never reach us. The observable universe is all we'll ever be able to see, even if we wait forever. In fact, due to accelerating expansion, the observable universe is effectively shrinking. Galaxies are constantly crossing this cosmic event horizon, becoming forever unreachable. The James Webb Space Telescope, launched in 2021, is revolutionizing our understanding of the early universe and its scale. It's detecting galaxies that formed just a few 100 million years after the Big Bang, some of which challenge our models of how quickly structures can form. JWST has observed galaxies like Galaxies 12, which existed when the universe was only 350 million years old. These ancient galaxies help us understand how matter was distributed in the early universe and provide clues about the universe's overall size and structure. One of the most mind-bending possibilities comes from string theory and its prediction of extra dimensions. While we experience 3 spatial dimensions plus time, string theory suggests there could be 6 or 7 additional spatial dimensions, curled up so small we can't detect them. But some models propose that what we call the universe might be just a 3-dimensional brane floating in a higher dimensional space. Other branes, other universes, might exist just millimeters away in these extra dimensions, completely inaccessible to us except through gravity. The concept of the multiverse isn't just science fiction speculation, it emerges naturally from our best theories of cosmology and quantum mechanics. Level 1 multiverse is simply regions of space beyond our observable universe. If space is infinite, then somewhere out there, incredibly far away, there must be exact copies of our observable universe, including exact copies of Earth, and even you. The distance to your nearest identical copy, about 10 to the power of 10 to the 122 meters. That's a number so vast that it makes the observable universe look like a subatomic particle by comparison. Level 2. Multiverse consists of other post-inflation bubbles with potentially different physical constants. Each bubble universe might have different numbers of dimensions, different strengths of fundamental forces, even different types of particles. The spaces between these bubbles are still inflating, expanding so rapidly that the bubbles can never collide or communicate. Our entire universe, infinite though it might be, would be just one bubble among countless others. The many-worlds interpretation of quantum mechanics suggests a level 3 multiverse, where every quantum event branches reality. Every time a particle can go left or right, the universe splits, with one version where it went left and another where it went right. This would mean there are about 10 to the power of 10 to the 120 versions of our observable universe just from quantum events since the Big Bang. Each branch is equally real but completely inaccessible to the others. To grasp these scales, we need new ways of thinking. Scientists use a concept called the cosmological horizon, which comes in several types. The particle horizon marks the boundary of the observable universe, the farthest distance from which particles could have traveled to us since the Big Bang. The event horizon is the boundary beyond which events cannot ever affect us due to accelerating expansion. The Hubble horizon is where objects recede at light speed. These horizons define the limits of what we can know, see, or influence. Recent discoveries are pushing these boundaries even further. The Nanograv collaboration using pulsar timing arrays has detected what might be gravitational waves from supermassive black hole mergers throughout the universe. These waves have wavelengths of light years and periods of years, carrying information about the universe's largest structures. The European Pulsar Timing Array and the Parkes Pulsar Timing Array are confirming these observations, potentially opening a new window into the universe's true scale. The South Pole Telescope and the Atacama Cosmology Telescope are mapping the cosmic microwave background with unprecedented resolution, looking for evidence of collisions between bubble universes. Some scientists claim to have found circular patterns in the CMB that could be bruises from our universe bumping into neighboring bubbles before inflation ended. While controversial, these potential discoveries hint that our universe might be just one cell in an infinite cosmic foam. But here's what really boggles the mind. Even if the universe is infinite, it might still be expanding. How can infinity get bigger? The answer is that it's not the size that's changing, but the density. Imagine an infinite checkerboard where the squares keep getting larger. The board remains infinite, but the squares, representing galaxies, get farther apart. This is what's happening to our universe on the grandest scale. The Euclid Space Telescope, launched by the European Space Agency in 2023, is creating a three-dimensional map of billions of galaxies across 10 billion years of cosmic history. By measuring how galaxy clustering has evolved over time, Euclid will help us understand dark energy and dark matter, which together make up 95% of the universe. This invisible majority might hold clues to the universe's true extent. Consider this astonishing fact. Every cubic centimeter of space, even the emptiest vacuum, contains about 400 photons from the cosmic microwave background. These ancient particles have been traveling since the universe became transparent, 380,000 years after the Big Bang. The observable universe contains about 10 to the 89th of these primordial photons. That's more photons than there are atoms in a trillion Earths. The universe's expansion rate, known as the Hubble constant, tells us how fast space is growing. Current measurements give a value of about 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years of distance, objects recede from us about 70 kilometers per second faster. But here's the mystery that's shaking cosmology. Different measurement methods give slightly different values for the Hubble constant. This Hubble tension might indicate new physics or that we're missing something fundamental about cosmic scales. Gravitational lensing provides another tool for measuring cosmic distances and sizes. Massive objects bend space-time, causing light to curve around them. The Hubble Space Telescope has captured spectacular examples of this, including Einstein rings, perfect circles of light from distant galaxies bent around foreground galaxies. By studying how light bends, astronomers can map the distribution of both visible and dark matter, revealing the universe's structure on the largest scales. The cosmic web, the largest structure in the universe, reveals patterns that stretch our comprehension to its limits. Galaxies aren't randomly scattered through space. They're arranged in vast filaments, separated by even vaster voids. The Millennium simulation, which used supercomputers to model 10 billion particles over cosmic time, showed that this web-like structure emerges naturally from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. The largest voids, like the Botez supervoid, span over 300 million light-years of nearly empty space. When we talk about the universe's size, we must confront the possibility that size itself might be meaningless at the larger scales. Some physicists propose that space and time are emergent properties that only make sense at certain scales. At the quantum level, space might be a foam of probabilistic fluctuations. At the cosmic level, it might be something else entirely. The universe's true size might be a question like asking for the color of Wednesday, a category error that reveals our limited understanding. The Large Hadron Collider at CERN is probing the universe's structure at the smallest scales, which paradoxically tells us about the largest scales. By recreating conditions from microseconds after the Big Bang, physicists study the fundamental forces that shaped cosmic evolution. The discovery of the Higgs boson in 2012 confirmed how particles acquire mass, but it also revealed that the Higgs field might be metastable. If true, the entire universe could be in a false vacuum state, and the true universe might have completely different properties and scales. Dark matter, which makes up about 27% of the universe, might exist in dimensions we can't perceive. The Alpha Magnetic Spectrometer on the International Space Station searches for evidence of dark matter particles, while underground detectors like Xenon and LX look for direct interactions. If dark matter exists in extra dimensions, the universe might be far larger and more complex than our three-dimensional slice reveals. We might be like flatland beings, aware of only a shadow of reality's true extent. The universe's topology, its overall shape and connectivity, remains unknown. While locally space appears flat, globally it could have exotic properties. It might be shaped like a torus, a donut, where traveling far enough in one direction brings you back to your starting point. It could be a Klein bottle with no distinct inside or outside, or it might have a fractal structure with similar patterns repeating at every scale. The Planck satellite searched for signatures of unusual topology but found the universe appears simply connected to the limits of observation. Time adds another dimension to the universe's size. The block universe theory suggests that past, present, and future all exist simultaneously in a four-dimensional space-time block. From this perspective, the universe isn't just spatially vast, it's temporally eternal, with every moment that has ever existed or will exist being equally real. The observable universe would then be a four-dimensional hypersphere expanding through this eternal block. Recent observations of fast radio bursts, mysterious millisecond pulses of radio waves from distant galaxies, are revealing the universe's hidden matter. As these bursts travel through space, they're delayed by interactions with ionized gas. By measuring these delays, astronomers can weigh the universe, accounting for all the normal matter that's been hiding in intergalactic space. The CHIME telescope in Canada has catalogued hundreds of these bursts, each one a probe of cosmic structure across billions of light-years. The anthropic principle offers a different perspective on cosmic size. We observe a universe large enough and old enough for stars to form, heavy elements to be created, and life to evolve. In a smaller or younger universe, we couldn't exist to ask these questions. Perhaps the universe's vast size isn't arbitrary but necessary, the minimum required for consciousness to emerge and contemplate its own existence. Quantum entanglement suggests the universe might be more connected than its size implies. Particles can be entangled across any distance, their properties correlated instantly regardless of separation. Some physicists propose that space itself emerges from quantum entanglement. That distance is just a measure of how entangled or unentangled regions are. In this view, the universe's size is less about space and more about information and correlation. The simulation hypothesis poses an ultimate limit to these questions. If our universe is a simulation, its size might be determined by computational constraints rather than physical laws. The observable universe might be all that's rendered, with regions beyond the cosmic horizon existing only as potential until observed. This would make questions about the universe's true size meaningless, like asking about regions of a video game that haven't been programmed. Let's consider what we've learned from Type I supernovae, the standard candles that revealed dark energy. The Supernova Cosmology Project and the High-Z Supernova Search Team showed that distant supernovae are dimmer than expected, proving the expansion is accelerating. This discovery, which won the 2011 Nobel Prize, fundamentally changed our understanding of cosmic scale. It means the universe will expand forever, becoming increasingly cold, dark, and empty. The future of the universe reveals its true scale in the dimension of time. If dark energy continues its current behavior, in about 100 billion years, all galaxies beyond our local group will have vanished beyond the cosmic event horizon. Future astronomers will see only a single merged galaxy, the collision product of the Milky Way and Andromeda, surrounded by absolute darkness. They'll have no way to know that billions of galaxies once existed. The observable universe will have shrunk to just our gravitationally bound local region. In 10 to the 14th years, star formation will cease as all gas is either locked in dead stars or dispersed too thinly to collapse. The universe will enter its degenerate era, populated only by white dwarfs, neutron stars, and black holes slowly cooling in the darkness. In 10 to the 40 years, even protons might decay, dissolving all ordinary matter into leptons and photons. The universe would become an unimaginably vast, cold, empty space with only black holes remaining. But even black holes aren't eternal. Through Hawking radiation, they slowly evaporate, with smaller ones disappearing faster than large ones. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate completely. The supermassive black holes at galactic centers would last much longer, up to 10 to the 100 years. When the last black hole evaporates, the universe will enter its final phase, the dark era, an infinite expanse containing only sparse photons and leptons, approaching maximum entropy and absolute zero temperature. The Vera Rubin Observatory, beginning operations soon, will conduct the legacy survey of space and time, photographing the entire visible sky every few nights for 10 years. This unprecedented survey will detect millions of supernovae, billions of galaxies, and track how cosmic structure evolves over time. It might reveal whether dark energy is truly constant or changes over cosmic history, fundamentally affecting our understanding of the universe's ultimate size and fate. String theory suggests the universe might exist in an 11-dimensional space with 7 dimensions curled up at subatomic scales. But some models propose that during inflation, different regions of space might have undergone different dimensional reductions. Some regions might have 3 large spatial dimensions like ours, while others might have 4, 5, or even more macroscopic dimensions. The universe might be a patchwork of regions with different dimensional structures, each incomprehensibly alien to the others. The holographic principle, inspired by black hole physics, proposes that all information in a volume of space can be encoded on its boundary. This means the entire observable universe might be a holographic projection of information stored on a 2-dimensional surface at the cosmic horizon. If true, asking about the universe's size becomes even more complex. Is it the volume we perceive or the area of the boundary? The universe might be simultaneously vast and compact, depending on your perspective. Consider the mind-bending implications of cosmic inflation scale. During inflation, regions smaller than a proton expanded to larger than the observable universe in about 10 to the negative 32 seconds. If inflation lasted just slightly longer, say 10 to the negative 30 seconds, the resulting universe would be exponentially larger. Some models suggest inflation might have lasted much longer in other regions, creating universes so vast that our entire observable universe would be like a single atom within them. The cosmic neutrino background, formed just 1 second after the Big Bang, fills space with about 300 neutrinos per cubic centimeter. These ghostly particles barely interact with matter. Trillions pass through your body every second without effect. The observable universe contains about 10 to the 89 neutrinos, and they've been traveling freely for almost the entire age of the universe. Future detectors might capture these primordial neutrinos, giving us information from when the universe was smaller than our solar system. Gravitational waves are revealing the universe's hidden dynamics. LIGO and Virgo have detected ripples in space-time from merging black holes billions of light-years away. These waves travel at light speed, unimpeded by matter or radiation. Future space-based detectors like LISA will detect lower-frequency waves from supermassive black hole mergers, potentially from the edge of the observable universe. Each detection tells us about regions of space we'll never see directly. The square-kilometre array under construction in Australia and South Africa will be the world's largest radio telescope. With collecting area of 1 square kilometre, it will detect radio signals from the cosmic dark ages, the period before the first stars formed. It might reveal structures from when the universe was just a few 100 million years old and only a fraction of its current size. These observations will test our models of how the universe grew from microscopic to cosmic scales. The concept of pocket universes within black holes adds another layer to cosmic scale. Some theories suggest that when matter collapses into a black hole, it doesn't crush to infinite density but bounces, creating a new expanding universe inside. Our entire universe might exist inside a black hole in a parent universe, which itself might be inside another black hole, creating an infinite nested hierarchy. Each level would be causally disconnected but mathematically linked through the geometry of space-time. The philosophical implications of the universe's size challenge our very conception of existence. If space is truly infinite, then everything that can happen must happen somewhere. There are infinite copies of Earth where history unfolded slightly differently, where dinosaurs never went extinct, where Rome never fell, where you made different choices. This isn't science fiction, but a mathematical consequence of infinity. In an infinite universe with finite possible arrangements of matter, every pattern must repeat infinitely. The observable universe contains roughly 10 to the 80 atoms. While that seems enormous, the number of ways these atoms could be arranged is finite, though unimaginably large, about 10 to the power of 10 to the 80. In an infinite universe, once you travel far enough, about 10 to the power of 10 to the 120 meters, you'd find an exact duplicate of our observable universe. Travel farther still, and you'd find every possible variation. But here's where quantum mechanics makes things even stranger. The many worlds interpretation suggests that every quantum measurement branches the universe. Since there are about 10 to the 90 quantum events happening every second in the observable universe, the number of parallel universes created since the Big Bang would be 10 to the 90, raised to the power of the number of seconds since the Big Bang, roughly 10 to the power of 10 to the 107. Each branch is as real as ours, but forever inaccessible. The cosmic microwave background's temperature fluctuations encode information about the universe's size and shape. These tiny variations, about 30 microkelvins, represent the seeds from which all cosmic structure grew. The Simons Observatory in Chile's Atacama Desert is measuring these fluctuations with unprecedented precision, searching for signatures of primordial gravitational waves that would confirm inflation and constrain the universe's true extent. Dark flow, a controversial observation suggesting galaxy clusters are moving toward a specific region of sky, might indicate structures beyond the observable universe. If confirmed, it would mean the universe extends far beyond what we can see, with massive structures pulling on our visible galaxies from beyond the cosmic horizon. The Planck satellite data has been scrutinized for evidence of this flow, with debates continuing about whether it's real or a statistical fluke. The Copernican principle suggests we don't occupy a special place in the universe. If true, then what we observe should be typical of the universe as a whole. This means the universe likely extends far beyond our cosmic horizon, with similar distributions of galaxies, dark matter, and dark energy throughout. We're probably not at the center of a finite universe or near its edge. We're somewhere unremarkable in an incomprehensibly vast or infinite expanse. Time crystals, confirmed to exist in 2017, show that matter can exhibit periodic structure in time as well as space. Some cosmologists speculate that the universe itself might be a time crystal on cosmic scales, cycling through states over periods longer than the current age of the universe. What we perceive as the universe's size might be just one phase in an eternal oscillation through different configurations of space and time. The firewall paradox in black hole physics has implications for cosmic horizons. Just as black holes might have firewalls of high-energy particles at their event horizons, the cosmic horizon might have its own firewall. This would mean the edge of the observable universe isn't just a limit of vision, but a real physical boundary where the nature of space-time changes fundamentally. The universe's size would then be defined by these quantum gravitational effects rather than simple geometry. Observations of quasars, supermassive black holes feeding on gas in distant galaxies, reveal the universe when it was much smaller and denser. The most distant known quasar, J0313-1806, existed when the universe was only 670 million years old and about 7% of its current size. Yet it contained a black hole of 1.6 billion solar masses. How such massive objects formed so quickly in the early universe remains a mystery that might require revising our models of cosmic growth. The lithium problem highlights gaps in our understanding of the early universe's size and density. Big Bang nucleosynthesis predicts the abundances of light elements based on the universe's density and expansion rate in its first minutes. While predictions match observations perfectly for hydrogen and helium, there's 3 times less lithium than expected. This discrepancy might indicate the early universe was smaller or larger than we think, or that unknown processes operated during its first moments. The axis of evil, an unexpected alignment of temperature fluctuations in the cosmic microwave background with our solar system, challenges the assumption that the universe looks the same in all directions. If real and not a statistical fluke, it might mean the universe has a preferred direction or structure on scales larger than we thought possible. This could indicate the universe is smaller than assumed, allowing large-scale patterns to influence what we observe. Cosmic voids, regions with far fewer galaxies than average, can span hundreds of millions of light-years. The KBC void, which contains our local group, is 2 billion light-years across, one of the largest structures in the universe. These voids aren't completely empty but contain dark matter and dim galaxies. Their existence and size distribution tells us about the universe's large-scale structure and helps constrain models of its overall extent. The concept of eternal inflation fundamentally reshapes our understanding of size. In this model, inflation never truly ends everywhere. It continues eternally, with pocket universes constantly budding off like bubbles in an infinite champagne. Our observable universe would be just one bubble among infinite others, each potentially infinite in size internally. The multiverse would be growing exponentially forever, with new universes being created faster than you could count them, even if you could count at the speed of light. Recent data from the Dark Energy Survey has mapped over 200 million galaxies, revealing that the universe's expansion is remarkably smooth on the larger scales. But there are hints of anomalies. regions expanding slightly faster or slower than average. These variations might be evidence of structures beyond our observable universe, massive concentrations of matter whose gravity affects our cosmic neighborhood from beyond the horizon. The baryon acoustic oscillations, frozen sound waves from the early universe, provide a cosmic ruler. These ripples in galaxy distribution have a characteristic scale of about 490 million light-years, set by sound waves that propagated through the plasma of the early universe. By measuring these oscillations at different distances, astronomers can track how the universe has expanded over time. The Dark Energy Spectroscopic Instrument is measuring these patterns in 5 million galaxies, creating the largest three-dimensional map of the universe ever made. Consider the implications of quantum mechanics at cosmic scales. The uncertainty principle suggests that at the smallest scales, space and time become fuzzy. This quantum foam exists at the Planck length, 10 to the negative 35 meters. If you zoomed in on space itself, you'd eventually reach a scale where the concept of distance breaks down. The universe might be fundamentally discrete rather than continuous, made of indivisible units of space and time. The size of the universe might be countable in Planck units, approximately 10 to the 185 Planck volumes in the observable universe. The black hole information paradox connects to questions about the universe's ultimate size. If information cannot be destroyed as quantum mechanics demands, then every bit of information that falls into a black hole must somehow be preserved. Some theories suggest this information is encoded on the black hole's two-dimensional surface. Similarly, our entire universe's information might be encoded on its cosmic horizon. We might be living in a holographic projection where the true size is the surface area of the boundary, not the volume we perceive. Primordial black holes, if they exist, would be remnants from the universe's first fraction of a second. Unlike stellar black holes formed from dying stars, these would have formed from extreme density fluctuations when the universe was incredibly small. Some could be microscopic, others as massive as asteroids or planets. Their distribution would tell us about the universe's size and density in its earliest moments, potentially revealing whether our Big Bang was unique or part of a larger process. The Great Attractor, a gravitational anomaly pulling galaxies toward it at hundreds of kilometers per second, demonstrates that massive structures exist beyond what we can directly observe. Located about 200 million light-years away but hidden behind the Milky Way's disk, this concentration of mass affects galaxies across hundreds of millions of light-years. Even larger is the Shapley supercluster, which might be the real power behind the Great Attractor. These massive structures hint at even larger patterns beyond our observational limits. Cosmic strings, if they exist, would be one-dimensional defects in space-time, thinner than a proton but potentially stretching across the entire observable universe. They would be remnants from phase transitions in the early universe, like cracks that form when water freezes. No cosmic strings have been definitively detected, but if found, they would provide a direct connection to the universe when it was smaller than an atom. Their length and distribution would constrain models of cosmic inflation and the universe's true extent. The measurement problem in quantum mechanics becomes profound when applied to the entire universe. In quantum mechanics, systems exist in superposition until observed, but who observes the universe? Some physicists propose that consciousness is necessary to collapse quantum wave functions. If true, the universe's size and properties might be determined by the presence of observers. We might be living in a participatory universe where observation retroactively determines what becomes real. The cosmic web's filamentary structure reveals that matter isn't randomly distributed but organized into a vast network. Galaxies and galaxy clusters are connected by dark matter filaments, with immense voids between them. The largest known filament, the Hercules Corona Borealis Great Wall, stretches 10 billion light-years. Computer simulations suggest this web extends far beyond what we can observe, possibly infinitely, with similar patterns repeating at ever larger scales. Time dilation near massive objects means that time passes at different rates throughout the universe. Near the supermassive black hole at our galaxy's center, time runs slower than on Earth. Across the universe, billions of years might pass in some regions while only millions pass in others. The universe doesn't have a single age, but a complex tapestry of local times. Its size in the time dimension is as complex and varied as its spatial extent. The discovery of dark energy acceleration means the universe has a future horizon as well as a past one. Galaxies currently about 17 billion light-years away are at the edge of what we'll ever be able to influence, even if we could travel at light speed starting today. This creates what physicists call the affectable universe, the region of space we could theoretically reach or communicate with before cosmic expansion carries everything beyond reach. This affectable universe is shrinking every second, with about 20,000 stars passing beyond our future horizon every moment. The quantum vacuum isn't empty, but seethes with virtual particles constantly appearing and disappearing. This quantum foam exists everywhere, meaning every cubic centimeter of space contains infinite zero-point energy. Some calculations suggest this energy density should be enormous, 10 to the 113 joules per cubic meter, but observations show it's nearly zero. This vacuum catastrophe, the worst prediction in physics, might hint that our understanding of space itself is fundamentally flawed. The universe's true size might be meaningless if we don't understand the nature of the vacuum that defines it. Loop quantum gravity suggests space itself might be quantized into discrete loops at the Planck scale. If true, the universe isn't continuous but made of indivisible units of space, like pixels on a cosmic screen. The observable universe would contain about 10 to the 184 of these quantum loops. Asking about distances smaller than the Planck length would be like asking for a color darker than black, a meaningless question that reveals the limits of our concepts. The Hubble Ultra Deep Field, a photograph of a tiny patch of apparently empty sky, revealed over 10,000 galaxies in a region covering just 1/13 of the total sky. If the entire sky contains similar density, there are about 200 billion galaxies in the observable universe, but recent estimates suggest this number might be 10 times higher, 2 trillion galaxies. As we look deeper, we keep finding more, suggesting the universe's content is richer than we imagined. The cosmic censorship hypothesis proposes that singularities, points where physics breaks down, are always hidden behind event horizons. If true, the Big Bang singularity might be hidden behind a past horizon we can never observe directly. Similarly, the universe's ultimate size might be censored by horizons that prevent us from ever knowing whether space is finite or infinite. Nature might have built-in limits to knowledge, boundaries beyond which questions about size become unanswerable. Observations of the integrated Sachs-Wolf effect, subtle heating of cosmic microwave background photons as they pass through gravitational wells, reveals the universe's structure on the largest scales. As light from the CMB passes through galaxy clusters and voids, it gains and loses energy, creating patterns that map the distribution of matter across billions of light-years. These observations confirm that structures exist on scales approaching the cosmic horizon, suggesting the universe extends far beyond what we can see. The multiverse hierarchy proposed by Max Tegmark classifies different types of parallel universes. Level 1 is simply regions beyond our cosmic horizon. Level 2 consists of other post-inflation bubbles with different physical constants. Level 3 is quantum parallel universes from every quantum event. Level 4 includes all mathematically possible universes. If this hierarchy exists, size becomes an inadequate concept. We need new language to describe the scale of existence across multiple types and levels of reality. Gamma-ray bursts, the universe's most powerful explosions, can be seen across almost the entire observable universe. The most distant detected, GRB 090429b, occurred when the universe was just 600 million years old and much smaller than today. These cosmic lighthouses allow us to probe the universe's size and composition across most of cosmic history. Each burst briefly outshines entire galaxies, serving as a beacon that reveals the universe's structure along its line of sight. The Lyman alpha forest, absorption lines in quasar spectra from intervening hydrogen clouds, maps the universe's structure in 3 dimensions. Each quasar's light passes through hundreds of gas clouds, creating a forest of absorption lines that reveal matter distribution across billions of light years. The BOSS survey has used this technique to map the universe's expansion history over the past 11 billion years, confirming that dark energy has been accelerating expansion for at least 6 billion years. Cosmic topology remains one of the deepest mysteries. While the universe appears flat and infinite locally, it could have a more complex global structure. It might be a 3 torus, where traveling far enough in any direction brings you back to your starting point. It could be a Poincare dodecahedral space, where the universe consists of a dodecahedron with opposite faces connected. These exotic topologies would make the universe finite but unbounded, limited in size but without edges. The anthropic principle offers a resolution to questions about the universe's size. We observe a universe large and old enough for stars to form heavy elements, for those elements to form planets, and for life to evolve on those planets. In a smaller universe, we wouldn't exist to ask these questions. The universe's vast size might not be arbitrary, but the minimum required for observers to emerge. We see a big universe because only a big universe can create beings capable of contemplating cosmic scale. The concept of the observable universe itself is constantly changing. Every second, the observable universe grows by about 300,000 kilometers in radius, the distance light travels in that second. This means approximately 20,000 new stars enter our observable universe every moment. But paradoxically, due to accelerating expansion, more galaxies are leaving our observable universe than entering it. We're gaining local detail while losing cosmic context, like zooming in on a photograph while the edges fade to black. String theory's landscape presents a staggering vision of scale. The theory predicts 10 to the 500 different ways to compactify extra dimensions, each creating a universe with different physics. If eternal inflation explores this landscape, creating pocket universes with every possible configuration, then the multiverse contains 10 to the 500 different types of universes. Our observable universe, vast as it seems, would be an infinitesimally small fraction of this cosmic landscape, like a single atom compared to all the atoms in all the galaxies we can see. The Fermi paradox gains new dimensions when we consider the universe's true scale. If the universe is infinite, there should be infinite civilizations. Yet we see no evidence of them. One possibility is that the universe's expansion creates cosmic loneliness. Civilizations are forever isolated by expanding space, unable to communicate or travel between galaxies. We might be surrounded by infinite intelligence, all trapped in their own cosmic bubbles, forever alone despite infinite company. Measurements of deuterium abundance in distant gas clouds tell us about the universe when it was just minutes old. The ratio of deuterium to hydrogen was set during Big Bang nucleosynthesis, when the entire universe was hotter than a star's core. These measurements confirm our models of the early universe's density and expansion rate. The fact that we see the same deuterium ratio in gas clouds billions of light-years apart tells us the universe was remarkably uniform even when much smaller. The cosmic web's evolution simulated by supercomputers reveals how quantum fluctuations grew into the largest structures we observe. The Millennium XXL simulation tracked 300 billion particles over cosmic time in a volume 7 billion light-years across. These simulations show that the cosmic web extends far beyond what we can observe, with similar patterns repeating at scales we'll never see. The universe's structure is fractal-like, with clusters of clusters of clusters extending perhaps infinitely. Primordial gravitational waves, if detected, would carry information from the universe's first fraction of a second. Unlike light, which couldn't travel freely until the universe was 380,000 years old, gravitational waves have been propagating since the Big Bang itself. These ripples in space-time would tell us about the universe when it was smaller than an atom. The BICEP array at the South Pole searches for their signature in the cosmic microwave background's polarization. The edge of the universe, if it exists, would be unlike any boundary we know. It wouldn't be a wall or barrier, but perhaps a region where the laws of physics gradually change, or where space-time itself becomes undefined. Some theories suggest the universe might be like a Klein bottle or Mobius strip, surfaces with no clear inside or outside, no definable edge despite being finite. The universe's boundary might be everywhere and nowhere simultaneously. Dark matter's distribution maps invisible structures larger than anything we can see directly. Gravitational lensing reveals dark matter, halos extending far beyond visible galaxies. The dark matter web connecting galaxies might extend infinitely, providing the scaffolding on which visible matter hangs like decorations. The universe might be far more structured in dark matter than in visible matter, with vast, dark structures we can only detect through their gravitational effects. The quantum Zeno effect suggests that observation can freeze quantum systems. Applied cosmologically, this implies that consciousness might play a role in determining the universe's properties. The universe might be large because it needs to be observed to exist, and observation requires complexity that only emerges in large, old universes. We might be living in the minimum-sized universe capable of observing itself. Eternal inflation predicts that our Big Bang was just one of infinite Big Bangs happening constantly throughout an ever-expanding multiverse. New universes are being born faster than you could count them, even if you counted at the speed of light. The universe isn't a thing but a process, an eternal flowering of new realities. Asking for its size is like asking for the size of creativity or possibility. The question assumes boundaries where none exist. The information capacity of the observable universe, calculated from thermodynamics and quantum mechanics, is about 10 to the 120 bits. Every possible state of every particle, every possible arrangement of matter and energy can be described with this much information. If the universe is a computation, this is its maximum memory. But if space is infinite, the information capacity is also infinite, allowing for infinite complexity and infinite possibilities. As we reach the end of our cosmic journey, let's confront the most profound truth. The universe's size transcends human comprehension in ways that fundamentally challenge our notion of existence itself. We've measured the observable universe at 93 billion light-years in diameter, but this might be like an ant measuring its anthill and declaring it the size of the world. The true universe could be billions of times larger, infinitely larger, or so strange that size itself becomes meaningless. The James Webb Space Telescope is revolutionizing our understanding by discovering galaxies that shouldn't exist according to our models. Massive, mature galaxies appearing just 300 million years after the Big Bang suggest either the universe is older than we thought, or galaxy formation happens far faster than believed. Each new discovery doesn't shrink the universe. It reveals that what we thought we knew was just the beginning of a far grander story. Consider what infinity truly means. In an infinite universe, not only does every possible arrangement of matter exist, but it exists infinite times. There are infinite versions of you reading infinite versions of this script, with every possible variation played out endlessly. Somewhere there's a version where you stopped reading 1 word ago. Somewhere else you're reading this in a galaxy where the laws of physics are slightly different. Infinity doesn't just mean very big, it means everything that can exist does exist infinitely. But perhaps the most mind-bending possibility is that asking about the universe's size is like asking about the color of mathematics, a category error revealing our limited perspective. If consciousness is fundamental to quantum mechanics, if observation creates reality, then the universe's size might be determined by the act of measuring it. We might be participants in creating the very scale we're trying to measure. The future holds even more staggering possibilities. The Roman Space Telescope will survey billions of galaxies with Hubble's resolution, but 200 times its field of view. The extremely large telescope will see the universe's first stars being born. The square-kilometer array will detect signals from before stars existed. Each instrument will reveal new scales, new structures, new mysteries that make our current understanding seem quaint. Here's what fills me with awe. Atoms in your body have traveled for billions of years and billions of light years to be here now. You're not observing the universe from outside, you're the universe observing itself from within. When you contemplate cosmic scale, it's the cosmos contemplating its own vastness. The fact that arrangements of atoms can ponder the size of everything that exists is perhaps the deepest mystery of all. The universe's size teaches us humility and grandeur simultaneously. We're infinitesimally small in a cosmos that might be infinite, yet we're the only known arrangements of matter capable of measuring that infinity. We're specks of dust that have figured out the scale of the very thing that dwarfs us. Every measurement we make, every theory we propose, is the universe understanding itself better. Whether the universe is finite but unbounded, infinite and eternal, or something stranger than we can imagine, one thing remains certain. It's large enough to create beings capable of asking these questions. It's old enough for stars to forge heavy elements, for planets to form, for life to evolve, for consciousness to emerge, and for that consciousness to look back at the cosmos with wonder. The observable universe will continue expanding, revealing new galaxies at its edge, while others disappear beyond the cosmic horizon. Future astronomers might see a very different universe than we do, smaller in some ways as galaxies disappear beyond reach, larger in others as they peer deeper into space and time. The universe's apparent size depends on when and how you measure it. Perhaps the universe's true size is best measured not in light years but in possibilities. It's large enough to create black holes and butterflies, quasars and quatrains, galaxies and dreams. It's old enough for hydrogen to become human beings capable of measuring hydrogen. It's vast enough that somewhere other minds might be pondering these same questions, looking at their night sky and wondering if anyone else is out there in the cosmic dark. As you go forward from this exploration, carry with you the perspective of cosmic scale. When you face challenges, remember you're made of atoms forged in stars, living on a mote of dust circling one star, among hundreds of billions in one galaxy among trillions. Yet you're also the universe's way of knowing itself, a cosmic miracle of consciousness in an ocean of space and time. The next time you look at the night sky, remember that you're seeing only the tiniest fraction of what exists. Beyond the stars, you can see lie billions more. Beyond those lie galaxies, too distant for light to have reached us. Beyond those lie realms that might forever remain hidden. And beyond even those might lie infinities we can't imagine. The universe isn't just bigger than we think, it's bigger than we can think. If you made it this far, make sure to subscribe to the channel and give a thumbs up. Your support means a lot to me. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. The Big Bang may not be the beginning after all. In this mind-expanding video, we explore the latest scientific theories and discoveries that challenge the idea of the Big Bang as the true origin of the universe. See you there.